continue, we can now talk about data. So now we're going to get into more technical details, I suppose you could say, about the computer, how we look at data, and not just in terms of it being computer data, but in how we collect and order our data. What characteristics does it have, or do they have? And then how are they implemented in a computer, specifically in relationship to GIS and GIT. So if we look here, we have, we'll go through all of these concepts. We have the idea of scale. Now this is not the same scale that you see given on a map where it says 1 to 50,000, for example. It's unfortunate that we use the same word. This is also true in Swedish as it is in English, but it's the scale, the skala, have the same translations. So this, when we talk about scale here, in this case, we're talking about qualities of the data, and we'll get to this very, very soon. And then we have this concept of model, whether something is, whether our data are discrete or continuous, whether they exist in small packets or there's a continuous field, for example. The data type, this is quite often a word that gets changed with other words, but for now, let's say data type. We're talking about whether it is integer 1, 2, 3, 4, floating point 0.1, for example. But again, we'll look at this later on. And then there's something called structure, which is quite closely related to model, but not necessarily. There's a strong connection, but it's not absolute. And this is how our data is stored in a file on the computer, whether it is a raster, an image with lots of squares, or a vector, which consists of points and lines and polygons. Or there's another example specific to GIS. The raster and vector are used in other areas, but in terms of GIS, we have the TIN, the triangulated irregular network, for storing essentially a field elevation quite commonly as a form of vector. Triangles of data of linearly interpolated points, as it were, across Earth's surface. I'll show you a picture of that soon. And then we have the format. Again, format and type. These words tend to get mixed up a lot of the time. We're kind of lazy in our usage of these words, and they're perhaps not used properly everywhere. And they can actually change as well, depending on who you're talking to. But within GIS, and certainly on this course, we're going to say that data type is integer, floating point, etc., and format is the type of file, the specific type of file that is being used, whether that's a shape file or a TIFF for a raster, for example. So let's move on and look at the details of this. We'll start actually with discrete and continuous, because these need to be just clarified first of all, if you're not certain of what these mean. So if we have discrete data on the left here, we have these discrete packages of data. So if we're looking at from the side, if this is for example, elevation, or it could be the amount of something growing in a field, or precipitation in a particular area, and it exists in these discrete packages. Over this entire area here, we have one value, and it's the same. We don't know where we are. We don't. It's just in this particular area, this plot of land, or in this piece of the Earth that we're looking at, that this one value exists over that entire area. It's homogeneous across that area, and then to get to the next piece up here, we have to jump up. There is no way, we can't continue along the line. We have to jump up or jump down if we're going that way to get to this next homogeneous surface. And these exist in these discrete packages. Jump down to the next one. There's no line connecting them. They happen to coexist next to each other if we were to look from above, but we cannot, there's no direct connection. We have to jump down and jump up across here. And then we have the continuous variant, where we can actually follow the line along, all the way along. We don't have to lift the pen off the paper, as it were. We can draw a continuous line representing the data. Wherever we stop, there is some way of moving without having to make one of these jumps to get to the next point along, the next point along. And this we can zoom in as far as we want and it will be still be there. That is the idea of continuous data. The truth of this is a little fuzzy when it comes to computers, but this is essentially the two distinctions we're going to try and make. How we normally conceptualize the data, how it's actually implemented in the computer is another matter. Computers don't like this sort of thing over here, they like this sort of thing over here. There's a big clue there, but we can conceptualize data as having these qualities of having continuous qualities, and we can conceptualize the data as having discrete qualities. On the computer, everything becomes discrete. That's just the way they work. But the packages of discrete data are so small, we say, that it looks continuous. So it is how we perceive the data that makes it continuous. Mathematically, how we treat it also looks perhaps at first glance to be continuous, although it will actually be discrete. But these are advanced concepts. But if you can think about something as being continuous, as having always some way of keeping your pen on the paper, as it were, then that is continuous data. If there is nothing in between, which we will look at when we're in the next slide, what that might mean, then it's discrete. Sorry, the slide after this one. So data type, just to clarify this, we have data types where we're describing how the information about a specific quality is stored, and this might be a value such as elevation. Are we going to store it as an integer value, 0, 1, 2, 3, 4, 5, with nothing there in between, or perhaps floating point numbers, decimal numbers, whereby we can hack up the distance between the different numbers into infinitesimally small pieces, depending on how many zeros we want to put in there. This is also limited by the storage on the computer, of course. But we have this idea of floating point numbers, where we can there is something in between these steps here. There's all of this information in between. But we can also store the data as text, for example. So we can write the numbers. We can write words, obviously, but we can even write numbers, write them out in letter form, or even numbers as we see them here. Strictly speaking, for the computer, this is text. It's not actually the number itself. It's a textual representation of that number. Not terribly dissimilar to these representations. This is specifically in English, and this is regardless of language, generally speaking. Everybody understands that is a 2. You might not understand that as a 2. That's just some thing, weird characters if you don't speak English, whereas that is still a 2. But for the computer, it's just text. It's a character. This is an important point. This also is an important point, this signed integer, that we have negative values, and the floating point that we have all of this potential to save all of these zeros. It requires space on the computer. Now, space on the computer nowadays tends not to be too much of a problem. The hard disks that we use are large in comparison to only a few years ago, but still we have a bottleneck when it comes to transferring data from the hard disk to the processor. That takes time. So we really need to think about how much space our data needs. Do we need all of these zeros? If, in actual fact, the only thing we're trying to store is 0, 1, 2, 3, 4, 5, then store 0, 1, 2, 3, 4, 5, because it takes less space for the computer to store this than it does to store this, 0.0. That takes a lot more room, because in actual fact the computer isn't storing just 0.0, it's storing 0.00, many zeros that we're just ignoring. And this all needs to be read into the processor or transferred over a network, moved around in between different parts of the computer, and that slows things down. And when we start working with larger and larger files, which we will do, especially when it comes to things like remote sensing, this can rapidly blow up, and especially as soon as when you try to perform some operation on the data to bring out more information, this can really slow you down if your data is stored in an unnecessary detailed data type. But the big and text is perhaps the worst in that sense, in that because we need to code every last thing as a text character, Imagine if we wanted to put that in as text, 0.0, we need to store a text part for this, a text part for this, a text part for that. It becomes very, very large. We can read it, which is the huge advantage. It's human readable, but it takes up a lot of space. So let's try and put all these things together. This was the slide I was thinking of earlier, how we combine all of these things and try and sort of see how they interplay. So back to this word scale, this slightly problematic thing where it's not 1 to 50,000 or 1 to 100,000, but we're talking about these different types of information scales, data scales. So what do these words mean? And what do they mean in relation to our model or our data type? We'll ignore the file types, file formats for now. We'll look at this in terms of our scale. We begin on the left, work through column by column, although actually some of the explanations will be easier to understand when in reference to other columns, to see what they're not as well as what they are. So we'll start with nominal, nom, name. We're naming things. So oats, rye, wheat, just things. This is a Trevor, and that's a Claire, or whatever names we're going to use. I don't know why I chose those names. So we have our discrete model. There's nothing in between oats. There's nothing in between rye. They exist as things, and perhaps these are fields of these things. And yes, okay, we could imagine that there's a little bit of rye crept into the oat field and a little bit of oat crept into the rye field, but we'll ignore that and just say they're discrete packages of this thing here. So they're nominal, they have a name, and they're either are or they're not, and we can draw a boundary between them. Each of these things has a distinct boundary around it, defining it. It exists in this place and not outside of that place, at least not nearby. So we don't really have a continuum of data. There's not any way of going from one to the other without jumping over a gap. So it's discrete data rather than continuous. And how would we store this? Well, text is a good way, storing the names, oats, rye, and wheat. But we could also store it as an integer. So in our file, in our large data file covering an area of land, we might just store it as 1, 2, 3, 4, and then in a separate file, a table, where we translate those numbers into what we actually mean. So 1 could be equal to oats, 2 could be rye, 3 wheat. And we have many of these patches with oats, rye, and wheat distributed across our landscape. And rather than having to store the word or these words each time for each package, we just store 1, 2, 3, whichever number we're using. So we save space in our data storage because we only need to translate that at various stages when we're trying to examine the data, when we want to visualize it on the screen and look at it. So we only need that translation to occur occasionally. The data itself can be stored as integer. That's quite efficient. But we can obviously store it as text straight if we don't want to have that ambiguity in our data. And then if we look at, say, ordinal data, now this is also discrete packages, but they have a particular order. Now it may be that you think oats are yummy and rye is not very nice at all. Wheat is somewhere in between. And so you could order those. You could put them in an ordinal scale. So 1, 2, 3, good, gooder or goodest. Obviously, that was not correct English. But we have first, second, third, fourth, like in a race. We have athletes running in a race. The person who comes in first wins. The person who comes in after them comes in second place, and after that comes third place. How fast did they run? That we haven't said. All we're caring about is the order in which they come in. It could be that the person winning wins, they're miles ahead, and then second and third and fourth come in a big group afterwards. We haven't said anything about that. We don't care. We just want the order in which they come. So we can store them in an ordinal scale. Typically, first, second, third. Small, medium, large in clothes. What is the actual size difference there? Is it linear or something else? Difficult to say sometimes. But we still know that one is larger than the other. So they have this ordinal scale. And again, we can store that. Perhaps it's even more intuitive to store it as an integer there, because those numbers even tell us something about their position. Of course, we need to get the the order correct? Is 10 worst or best? Are we going up or down? That's another matter. But we can also store it as text, obviously. So let's move on to the next column. And here we said with the ordinal, we didn't describe a difference. We didn't describe the distance between these first, second, and third. In an interval scale, we do. We say that things happen there's a distinct distance, as it were, between, it could be in time, it could be in volume, but anyway, we have the step from, or the transition from being 2 to 3, and from 3 to 4 is equally long. These steps up, or the distance along this continuous line, is the same. From 3 to 4 is the same distance as from 2 to 3. But you arrive at a different place. So here we can see we actually have this. We move over into having a continuous model because we can exist along this continuous gradient. We can move along. The distance to 2.5 is the same from 2 is the same as the distance from 3 to 3.5, or back again. It's the same distance. That's our interval scale. And what's the difference then between an interval scale and a ratio scale? Because they look very similar. Well, the ratio scale has a true 0 point, whereas the interval scale doesn't. This is exemplified here with centigrade. If we compare centigrade to Kelvin, so degrees centigrade, 0 degrees centigrade, the freezing point of water, is not a real zero, in that say 20 degrees centigrade is not twice as warm as 10 degrees centigrade. It's just 10 degrees warmer, 10 degrees centigrade warmer. Whereas if we use the Kelvin scale, 0 Kelvin is as a physical quality of being 0, that we have no temperature. Well, there is a temperature. There's a temperature of 0 Kelvin, but there's the entropy in the end. Well, it's a proper 0, and if we then go to 10 Kelvin and then to 20 Kelvin, 20 is twice as much of this thing that we're talking about as 10 Kelvin is. And that happens that a Kelvin, 1 Kelvin, happens to be the same size as a degree centigrade or Celsius, however you want to express it. It's just that the centigrade scale has no proper 0. The 0 is just an arbitrary point. We can move along it in these steps, and each step is the same distance, but we are limited to the mathematical operators that we can perform on it. In the interval scale, we can move along that line in even steps. We can add and subtract step along, but what we cannot do is multiply. As I said, 20 degrees is not twice as warm as 10 degrees centigrade, whereas we can take 10 Kelvin and multiply that by 2, and we get to 20 Kelvin, and that's a meaningful operation. We can exemplify this perhaps if we look at distance. So a ratio, if we're moving along, we start from a 0 point and we move 10 meters, and we want to double our distance. We can multiply 10 by 2 and we get 20 meters, and we are twice as far away. This is actually, we can now look at another example of the difference between interval and ratio scale that is quite tricky, and we have to keep these things clear in our heads. When we look at coordinates on a map, they will have a 0 point. There is a 0, and it's a genuine 0, as it were. So we can move along from that 0. We can double our distance along it, so that we're twice as far along the easting axis as we were. So we were once at 100 kilometers. Times that by 2, we're at 200 kilometers from our 0 point. But quite often when we look at a map, we don't have the 0 on there. That's somewhere else. Our map is some portion. So it's very difficult then to double our distance. If we're just working within the frame of the map, and we have a coordinate on the map, and we measure the distance and then measure another distance farther along that is twice as long, we can't use the coordinates. We can calculate, we can see the difference between them, but we can't multiply the coordinate along the x-axis of the first one by 2 to get twice as far along as far as we are concerned on that map. We would be twice as far along from the origin, which is outside of our map, and we'll end up way outside on the other end of our map if we multiply that first coordinate. So coordinates are actually a little bit of a pain because, well, they're a bit tricky because they are actually truly a ratio scale because they have a proper zero and we can multiply them. But as we typically use them on a limited, within a limited frame on a map, they behave more like an interval scale. That's convenient, isn't it? But it's not actually a problem. Just remember that the interval scale turns up here and there, and what we can do is we can step along the line. We can in these steps we can plus and minus, or it also works as a continuous scale, but we have to move along regularly along that line. We can pass along it as we do normally in space and time. Whereas the ratio scale, here we can do these magic things whereby we can divide and multiply, and suddenly we get twice as much or half as much, for example. So the ratio scale has a true zero, and we can perform these multiplying factors. That is distance, for example. I hope that's kind of clear. Think about these things. This is perhaps the one that feels more familiar, really, in the end, the ratio scale. And the interval scale is where you get tripped up. The interval scale is where you make mistakes because things actually, in the way you're using them, turn into an interval scale because you don't have a genuine zero. It's quite often the way it works. Not always. Some things are naturally interval scales. Positioning being one of them, depending on what you're talking about. But so be aware and think about these. I think that's the best we can do there. And then I've stuck on the end something called Boolean, just to introduce it as a concept. This is a condition very familiar to the computer, whereby things exist or not. They are true or they are false. Yes, no. This can be represented down here by a 0 or a 1, which is why computers love them. It's a switch. The switch is on or the switch is off, or off or on, depending on how you want to represent these things. So 0 and 1 being the state that a computer loves to work with. And so we have this state, but Boolean can also be replaced. We can get this continuous version of something that's not truly Boolean now. We're moving into something called fuzzy logic, whereby something sort of is or sort of isn't, but to what degree? So if we abandon the idea of truly Boolean and move over into fuzzy logic instead, then we can get this continuous model. But strictly speaking, the Boolean yes/no is discrete. So this should actually be in parentheses, really, because it's not strictly speaking the same thing. But this is how we can take our information about the state of something, whether it is or isn't, and represent it. So I think we'll end that part of the lecture there.